Section 1.1 is about functions and continuity in Algebra 2. The first thing we're going to do is identify some vocabulary that you've already seen before. Domain. Domain is going to be all of the x values that would be possible from your function. The range is all of the y values that are specific from that function. Your codomain will be something that is new. Your codomain are the y values that are possible from the function. So these are going to be the exact ones that you see or that you can see from the graph or the table, but this one is going to be whatever is possible. So in that case, it's always going to be all real numbers, so that will be your answer every time, unless they specify something else. So for example, they might say y is less than 2. Let's look at some examples to see what that would look like. So in this example, they want us to identify the domain, the range, and the codomain. And then they're going to ask if it is onto. Well, first I'm going to identify the domain. So what are all the possible x values? So as I look at this graph, I can see that I have all of these x values along here, and I also have all of these x values along here because I can go up here and I can see exactly where my x's are going to be without drawing them. So your domain is going to be all real numbers in this case. Your range is what is possible for your y. So think about where your y's are starting. Well, as I look at my graph, my y values are starting at 0. And I see that my y values are getting less than because my graph is pointing down. So in this case, my range would be y less than or equal to 0. Now it doesn't specify what my codomain is going to be, so in that case, my codomain is all real numbers. If you don't like using this double-stemmed R, you can write out the phrase all real numbers. Now this is a new vocabulary word, and it's onto if your codomain is the exact same as your range. So if those two are the same, then it is onto. So in this case, since they are not the same, then it is not onto. I want you to pause the video and try the next example. So in the next example, it's the same thing. So in this case, your x's are all negatives and all positives. So again, it would be all reals. Your range would be your y values. Your y values are also going to be all reals because it's encompassing the negatives and the positives. And then your codomain is not specified again, so it would be all reals. In this case, it would be onto because my range is matching my codomain. All right, we went ahead and identified or defined what an onto function is. But one other definition that we would need to do is called one-to-one. And that is the case in which each element of the range is paired with exactly one element of the domain. So you're looking to make sure that the range is not duplicated. Okay, so your y values cannot be duplicated in order for it to be one-to-one. So let's look at this first example. So it says determine whether the number of gold medals is one-to-one, onto, both, or neither. And we will do it for silver and for bronze. So your domain is going to come from the years. Okay, and we're going to start with just the gold medals. So this is going to be your range. So first off, if I'm one-to-one, I cannot have any duplications. So this would be an example of not one-to-one because I have two 46s and two 36s. So I can't have that duplication. Onto, remember, is that your range has to match your codomain. So here was my range, these numbers. I don't see a specification for my codomain, so my codomain was all reals. So since those are not the same, this would be not onto. So since it's neither of those, that would be my answer. Now you're going to try the silver column. So I do the same thing. So my domain are my years. My range is all of the silver column. Okay, so in order for it to be one-to-one, I can't have any duplication. So I'm looking through here. I don't see any duplication, so that is 1 to 1. Same as before, my range has to be the same as my codomain. And my codomain, we already said, was all real. So since those are not the same, it's not onto. So therefore, my answer is just 1 to 1. You're going to pause the video and try the bronze column. In the bronze column, you should have figured out that it was 1 to 1. No duplication of your y values, and my range numbers is not matching my codomain. So therefore, it is not 1 to 1, and it is just 1 to 1. Okay, now let's look at some graphs. So the next part of this is determine whether it's 1 to 1, onto, both, or neither from the graph. Okay, so in this case, when you are looking at the graphs, you're going to want to do a horizontal test. And if your line that you are looking across horizontally crosses more than once, it would not be 1 to 1. Okay? And then we already know the definition for onto as well. So I can see that none of my y values are duplicating because as I look through here, my horizontal test shows that it's only crossing one time. So I know that it's going to be 1 to 1. It tells me my codomain is all real numbers. And as I look at the range, I see that my graph is not going below 0 for my y values. So that tells me that my y values are starting at 0 and they are getting bigger because my graph is increasing. So my range would be looking like that. Since these two are not the same, that is not onto. So in this case, it would just be 1 to 1. Let's try another example. I'm looking to see if it's 1 to 1, so I'm going to do that horizontal test to see if I have any y values that are duplicating. And as you do that, you should see that when I do that horizontal test, these two spots and these two spots both have the same y value. So in this case, it would not be 1 to 1. Your codomain is already shown right here. Y is less than or equal to 4. So now I need to look at the graph and determine what is my range. Well, I see my graph is starting at y equals 4. And I see it's pointing down, so that means all of my y values are going to be less than 4. So therefore, since these are the same, that would be onto. Now the next two do not specify the codomain. So if it's not specified, remember what it's going to go back to. So in this one, I know my codomain is all reals. And the same for the last one. So pause the video and see if you can try those last two. So on the third one, you should have figured out that it was both. As I look through my horizontal test, my horizontal lines will only cross through one time on each part of that curve. So therefore, it is 1 to 1. And as I look for onto, my codomain was all reals. And as I look at my range, I see that I am doing above 0 and below 0, so therefore it is also all reals. So it is onto and 1 to 1, so that's why it is both. Now looking at the very last one, still codomain is all reals because it's not specified. I look at my horizontal test, and as I look through it, right here I see that it's crossing more than once, so therefore it is not 1 to 1. Then I'm going to check my codomain with the range to see if it's onto. My range looks to be, let's see, my graph is going above 0 for the y values, and it is going below 0. So therefore, my range is all reals. So in this case, it is onto. All right. Continuing, that finishes the first part of section 1.1, but we're going to continue on to the second part, even though we break it up over 2 days here. So on the second part, what we're going to cover is discrete and continuous functions. So defining a discrete function just means it's discontinuous, so that means your points are not going to be connected with lines. Continuous functions means it's an unbroken curve, so there will be a line connecting all your points. If you're going to decide if it's neither, that means it's going to be a combination of both. Like you'll see some lines being connected to the points, and then you'll have some points that will have no lines connected. So our first task is we have to determine if it is continuous, discrete, or neither, and then we have to identify our domain and range again. So in this case, see how my curve is connecting all my points and there are no breaks? That would be an example of a continuous function. Then it wants me to identify the domain and range again. Well, as I look to the left and to the right, I see that my curve is to the left of the 0 and to the right, so therefore it is all reals for my domain. And the same for my y's. I see my graph is below 0 and above 0, so therefore my range is also all real numbers. On the second example, this is a combination. I see a line connecting all the points, but I also see one broken part out of there. So this is an example of neither, because you have that line and then you have that broken part in the curve. This one's kind of tricky. So this broken part means that's not part of my graph. So for my x values, what I'm going to need to know is where this point is. So this point is at 2, 1. So that means I'm using all of my x values that can be left of 2. So therefore, I can be all of my numbers to the left and to the right except for 2. And this is how you can write that. All reals, and then x cannot be equal to 2. Same would have to be said about your range. It can be all of your y values except for that point. So you would write all reals except for y equaling 1. Pause the video and see if you can determine the last one. So on the last one, there are no lines whatsoever. So that's an example of a discrete function because it's just points. And when it's just points, then that means you're just going to have specific numbers for your domain and range. So for example, domain is all of my x coordinates. So I had -3, -2, -1, +1, +3, +4 for all those x coordinates. And your range is going to be all the y values of those points. So this was -3, -2, +1, +2, +3, and then I must have missed something, +4. I think I went in the wrong order, but you get the idea. Okay, so you're just listing the x coordinates of those points and the y coordinates of those points. You're just seeing how to write that part. Okay, an application problem here. So use the given information to determine if the scenario is discrete, continuous, or neither, then state the domain and the range. So they're showing you that you've got a coffee shop up to 2 pounds, it's $8 a pound. You can buy exactly 2.5 pounds at $20, 3 pounds at $22, 5 pounds at $35. Down here at the bottom, Cafe sells coffee beans by the pound up to 2 pounds, and for larger amounts, they sell just the pre-packaged bags. So the important part is trying to decide is it discrete, continuous, or neither. This is an important part. If it's saying that they will get you up to 2 pounds, I could buy 1.1, 1.3, 1.5, and I can go all the way up through 2. So that's going to be a continuous curve. But then once I jump out of 2, then it's just going to be these points. So this is going to be a combination of both, which is why it would be neither situation. And then if they wanted you to state the domain, it would be that same thing. My domain would be the weight, and my range would be the price. So how do I write up to 2 pounds? Well, the lowest amount I could buy would be 0. So I can write 0 is less than or equal to x less than 2. And then I can add to it, I can be x equal to 2.5, x equal to 3, and x equal to 5. So these are just specific points. Same with your range. My range can start at 0 and go all the way up through $16 because it's $8 a pound, so that would be 8 times 2. And then I would have these specific points, 20, 22, and 35. So just trying to make sense of it in a real world application of what you were just kind of discussing. All right, the other big portion of this lesson is set builder and interval notation. So set builder, how you're going to write it is you're going to put an X, then you're going to draw a line, which when we read it says X such that, and then you're going to write some kind of inequality over here. So here's an example, X such that X is less than 3. That would be set builder. Interval notation is where you get to use parentheses and square brackets. You're going to use parentheses if the endpoint is not included and square brackets if it is included. So anytime we write infinity, it's always a parenthesis because we don't know where it would stop. So this is an example of I'm going all the way from negative infinity to positive 2, and positive 2 is included because of that square bracket. So let's practice writing some of that. So write the domain and range in set builder and interval notation. So once again, we've been practicing domain and range, so I can see that my X values, I am less than 0, and I'm also right. So that means I'm using any X values I want. So anytime you write it as all real numbers, you write it like this for set builder notation. So I would start with an X, do my such that line, and then X is an element of all real numbers. Okay, so that E right there is showing you that X is in that set. Then for the range, just keep going with that same thing. I also see that my Y values are above 0 and below 0, so it's going to be the same format. Whoops, I'm sorry. It stops at negative 6 here. So I would still write with my Y here, but now I'm going to change it to what that interval would be when we would write it. So I'm starting at negative 6, and I can be greater than or equal to that spot. So when you change to interval notation, here's where you get to use those infinity symbols. So interval notation, if I'm any real number, that means I could be negative infinity, and I can go all the way through positive infinity. So we always use regular parentheses when we have that infinity symbol. So anytime you say all real numbers, this is how you would write it for interval notation, and this is how you would write it for set builder notation. Since we started at negative 6 on this one, it's a little bit different. So I'm starting at negative 6, which is why I'm doing a square bracket, because it is included. And then I'm going up, so that's going to go up towards positive infinity. And then I'm doing a regular parenthesis again because of normal, because of infinity symbol. Pause the video and see if you can try the next question. So on the next question, we're still writing domain and range. In this case, I see that my X's are going left and right of 0. So that tells me that we're going to have X as an element of all real numbers. In this case, I see my Y values starting at 0 and getting less than that. So I would write Y such that Y is less than or equal to 0. Now I'm going to think about how to change it into interval with my infinity symbol. So all real numbers means I'm going to go from negative infinity all the way through positive infinity. This case, I'm reading left to right. So my negative infinity is going to go first, and then it's going to range all the way through 0 with that square bracket. When you're writing these, you want to think about a number line, and we read them left to right. So that's why we're putting that negative infinity symbol first, because we're reading the negatives first as we move across the number line, and then 0 is where we're stopping on the right-hand side. So it is important that you're listing it like that. We're going to continue to practice this, but now we're going to change to some discontinuous functions. And so in this case, they're going to get a little bit more difficult only because you have to think through what your domain and range are going to be. So in this case, I see that we have it starting here at 1, -1, and this point is at 0, 2. So I can see that my X values are going to be at 1, but they're getting less than 1. So that's why I'm going to write it as x less than -1. And notice I didn't put an equal sign because of that open circle. Then you're also going to put the word or. I can also be at 0 and I can be increasing. So I can be x greater than or equal to 0. Now notice I put the equal sign because of the closed in circle. Now continuing on to your range, kind of the same scenario, but just different numbers. So I'm going to be y is less than -1 because I'm looking at my y values, and I'm going to be y greater than or equal to 2 because again I'm looking at that y value. Now, when you change over to interval notation, we're going to write both of these. So for this one, I'm going to be at -infinity and go all the way up to -1. And it's not included, so I'm going to use just a regular parenthesis. So for this or, what we're going to do is use this symbol where it's just a U. Okay, that's showing it is just an or word. And now I'm going to do here. So now I'm starting at 0. So I'm doing a closed bracket because it was included. And then I'm continuing on to positive infinity. And so for your last one, you're going to do similarly. Start at -infinity, go all the way up to -1, and then or with that U, enclose 2, and then go all the way up to positive infinity. Once you practice this enough, I feel like you kind of get the hang of it. So pause the video and try this very last one. So on the last one, here's what you should have gotten. You should have said that your x's will be at -1 or less, okay, because I don't have anything bigger than -1, or I have them starting at +1 and being greater than, so x greater than or equal to 1. Now for your range, it's encompassing all those y values, so y is just an element in all real numbers. So when you do interval notation, we're doing -infinity going all the way to -1.
Sorry for the interruption.
And enclose it.
Staff, please help ninth graders with their lockers and to get out to the bus.
+1 through positive infinity.
Afternoon. Remember, you
and
only
then
have
all
2 or
real
3
numbers
minutes to make the bus.
Goes like
Thank
this
you.
for -infinity and positive infinity. Okay, so section 1 is very long, a lot of different things in there with a lot of different vocab, one-to-one, on-to, set builder, interval notation, domain, range, codomain, just a ton of vocabulary. So just take your time with it and we'll work through it. Section 1-2 is about linearity, intercepts, and symmetry. So the first thing we're going to do is decide if a function is linear or not. A linear function can be written as y equals mx plus b. So when you have an equation, it would be y equals some number x plus some number. As far as exponents goes, in order for it to be linear, your exponent has to be a whole number and it has to be less than or equal to 1. So if this is x or there's no x in there, that would be an example of it being linear. Nonlinear obviously means it's not linear. So first thing we're going to do is look at some equations and see if it's linear or not. So for letter A, first thing I see is that my exponent is a 1. So that checks off that box. Then I would check to make sure this is in the form of y equals mx plus b. Well, even though it says f of x, that can still be written as just y equals. So this would be an example of linear. Letter B. First thing I do is check for my exponents. I see my exponent is 3. That's above 1, so this would be an example of non-linear. Letter C. This one's a little different because the x is in the denominator. So even though the exponent is a 1, you would need to rewrite it so that the exponent became, just trying to zoom in so you can see that better. The exponent would have to go, or the variable would have to go to the numerator in order for it to qualify. So if it's in the denominator, when it moves, it becomes negative. So this is technically the form of it. So since this exponent is less than 0, that wouldn't work. So I guess I need to rephrase that definition, making sure that it's not less than 0. So this would be an example of nonlinear. And then last, letter D, I would check my exponent on x is 1. And then I can rewrite this into slope-intercept form. I can minus my 3x over. And then I can divide everything by 2. So this would work as being linear because it would have an exponent of 1 and then also have that form as to y equals mx plus b. You're going to pause the video and try the next question to see if they are linear or nonlinear. So on the next question, you should have figured out that this first one would be linear because I have an exponent of 1. This one would be nonlinear because of the fact the variables is an x and a y, so that one's kind of tricky. This one is like the last example. This one is linear because I can change it into y equals mx plus b. This one's a little different because it's just y equals 5. So there's not a variable there, and that's okay. So as long as it's just y equals, that's considered to be linear. Nonlinear for this one because I have an exponent bigger than 1. And this one would be linear. This tries to throw you off because of the square root of 3. But remember, your exponent has to be 1 or 0. And then it's already in y equals mx plus b. So that one would be linear. Okay, now we're going to look at some graphs to see if they're linear or nonlinear. And that just goes off the name, right? So if I am linear, then that means for my graph, I would be a straight line. If I'm nonlinear, it's not a straight line. So in this first graph, it would be nonlinear. And in the second graph, it would be linear because even though they're not connected, it could be drawing a straight line all the way through there. All right, pause the video and try the next question. So in example 2b, you should have figured out that A is linear, B is nonlinear, C is nonlinear, and D would be linear. So because of these two making straight lines, that makes them linear. These two were all curvy, so that is why it was nonlinear. All right, moving right along. Next part we're going to talk about is what does it look like when you are in table form. So to determine if it's linear, it has to have a constant rate of change. So what you're going to do is you're going to check to see if the rate of change of the y's is staying consistent. So in this case, this one is always adding up by 34. And how I found that was just subtract the bigger number by the smaller number. So since there's a constant rate of change, this is an example of a linear function. Pause the video and try the second table. So in the second table, it also is linear because you are consistently changing by negative 22. So my constant rate of change was that negative 22. All right, changing over to intercepts. So x-intercepts, y-intercept. So an x-intercept is the x-coordinate of the point where it crosses the x-axis. So for example, if this was my graph, this is an example of the x-intercept, but you want to just draw, you just want to write down the x-coordinate of that point. And the same for the y-intercept, it's where it's crossing the y-axis, but you want to just write down the y-coordinate of that point. So let's practice that. So in this first graph, you can see we have a straight line, and I went ahead and already drew in where my x-intercept and y-intercept were. They actually are the same point. So it's where it's crossing the x-axis and crossing the y-axis. So the coordinate for the x-coordinate would be 0, because it's 0 for that. And my y-intercept would also be at 0, because that's the y-coordinate of that point. Pause the video and try the next graph. So here you have two distinct points. So here's my x-intercept where it's crossing the x-axis. Here's my y-intercept where it's crossing the y-axis. So remember, I'm just writing down the x-coordinate. So my x-intercept would be at 3, and my y-intercept would be at 4. All right, so if you were here for class, we would be breaking this up into 2 days, but we will just continue on here. So on day 2 of this, we're going to use our graphs again to find our x and y intercepts, but they will not be straight lines. So in this case right here, my x-intercepts occur at 3 different points, and my y-intercept occurs at that point. So my x-intercept is going to occur at -3, -1, +2, and then my y-intercept is going to occur at 12. Pause the video and try the next graph. On the next graph, you should have a y-intercept at 1 and an x-intercept at 3, just utilizing those 2 points. Now, what does it look like when you have a table and a real-world example? So using the given information, identify the x and y intercepts, explain what they represent. So Ricardo launches a rocket from a second-floor balcony. The rocket is equipped with an electronic altimeter. The table shows the height given by the altimeter after each second of the rocket's flight. So remember on my graph, if I were to write down the coordinates of these points, so if I go back to the previous one, the coordinates of this point would be 3, 0. And the coordinates of this point would be 0, 1. So notice that your x and y intercepts always have to have that 0. Well, I can find that in a table by locating those zeros. You just have to pay attention to which one this is. So here would be an intercept, and here would be an intercept because the second coordinate is 0. Now, what you would want to consider is which one is it? Well, this would be the y-intercept because it's the y-coordinate, and this one would be the x-intercept because it's the x-coordinate. So those would be your 2 intercepts you would want to identify, and then just explaining what's happening. So after 0 seconds, I'm 15. I have a height of 15. Well, that just means when it started, I was at a height of 15. And after 8 seconds, my height was 0. So after 8 seconds, that's going to tell me that my rocket is going to hit the ground. All right, you're going to pause the video and try the next question. So on the next question, you should have figured out your 2 intercepts. My y-intercept is at 500. My x-intercept is 5. So at 0 weeks, I had 500 tickets. So that means that the junior class wants to sell 500 raffle tickets. Then after 5 weeks, I have 0 tickets. So that means it took me 5 weeks to sell all of those tickets. All right, next part of this lesson is even and odd functions. So this kind of goes in with end behavior, and end behavior are the tails of your function. So if it's an even function, that means your tails go the same direction. So what that means is you're going to have a function where the arrowheads are both pointing up or the arrowheads are both going to point down. If it's an odd function, the tails are opposite directions. So that means you would have one pointing down, one pointing up, or vice versa. One was up and then the other was down. So we're going to identify if it's even or odd, but there is one more part to it that you want to think about when you're looking at these graphs. So on this first one, I see tails are going opposite. So that tells me that this could be an odd function. Now, one thing you have to think about is that in order for it to be an odd or an even function, where these humps lie need to be symmetrical. So that means the distance to them have to be at the same spot. So this is at y = 3. This is at y = -3. So they're the same distance to the x-axis. So that would be considered as odd. So on this next one, notice my tails are both pointing up. So since they're going the same direction, I would consider it to be even. And again, I would want to check these humps and make sure that they're the same distance at those points so that they're symmetrical. So like if I were to fold this across here, that would end up lying on there. So this looks like it is about at 4.5, and this one looks like it's about at the same spot. So pause the video and see if you can try that last one. So on the last one, it looks like it's going to be odd because I have tails going opposite directions, But these humps are not symmetrical. So this one looks like it's going at about 2.2 because it's over 2. And this one is under 2, so at about maybe 1.8. So those are not symmetrical. So this would be an example of neither. So that's the only part that you have to check when you're seeing if it's even or odd. Okay, pause the video, I guess, and try another example here to see if it is even, odd, or neither. So I only have one hump, and so it does look like it's going to be symmetrical since I only have one hump. So this would be an example of even since I have the tails going both direction. All right, folks, that concludes section 1-2. So that was talking about linearity, intercepts, and then also even and odd functions based off their symmetry. Section 1-3 is about extrema and end behavior. So end behavior are those tails that we were just talking about in the last section where you were seeing if the tails or the arrowheads are both going up or both going down or opposite directions. And your extrema are like what happens with the maximum and minimums. So here we go. So we start with some vocabulary, and your extrema is what I just said. It's the maximum or minimums. So when you have a picture here, if I were just to draw you something like this, here would be a maximum in my picture because it's the highest point. Here would be the minimum because it's the lowest point within those humps, okay? So you're kind of looking at those hills and valleys, and your hills at the top of the hill is going to be the maximum, and at the bottom of the valley is going to be your minimum. Now, if you have several of those within a graph, then we have minimum and maximums, but then we also have relative minimums and relative maximums. So think of these as like the kings and these as the queens or the pawns, if you will, that are the second in nature. So for example, something like this. So this point here would be my maximum because it's one of the highest points. This would be considered my minimum. Then this would be considered a relative minimum because it was still a minimum, but it's not the lowest one. And then this one would be considered a relative maximum because it was lower than the maximum. Okay, so kind of second in charge, if you will. So what we're going to do first is just kind of identify what all of those are and try and find where those extremas are. So this first example asks you to identify your x and y values of the extrema. Well, this one's pretty easy because there's only one little curve, one little hump in there. So here is my valley. Okay, so since it's at the bottom of the valley, this would be an example of a minimum. And then I'm just going to write down the coordinates of that point. So it would be 0 and -5. Pause the video and try the next example. So in the next example, you've got a whole bunch of different humps, okay? So you should have these two as maximums and these three as minimums. Now, the true maximum is going to be 2, 6, okay? And then my true minimum is going to be -6, -7, because that is the lowest point of the humps in the entire graph, and this is the highest of the humps in the entire graph. Then the other ones you're just going to label as relative mins and relative maxes. So these are both relative mins because they are higher than what your actual minimum is. So 0, -4, 5, and -5. And then this one would be your -3, 2 as a relative max because it's still maximum, but it's not the highest maximum. So that's why we just refer to it as a relative max. Okay, then we have some story problems where we try and make sense of how do you use this extrema? Like, what do they do with this kind of stuff? So here's a word problem. I'll read it to you because it's kind of faded in there. So the number of posts sent on a popular social media site varies throughout the day. Move through the categories to see how to use the table and graph to estimate the extrema of the function that relates the number of hours since midnight x to the number of posts being uploaded y in 100,000s. Describe the meaning of the extrema in the context. So this is coming off of our online portion of our book. So there's really no table and stuff that you're clicking and dragging through. We're just going to find all of our mins, max, and relative mins and max. So I can see my maximum is clear down here, and my minimum is clear over here. And then I can also see I've got another minimum, but this would be a relative minimum because it's not the lowest point. And this would be a relative max because it's not the highest of my humps. So that's what I listed out here. I just listed all of those coordinates that I saw. Then I'm just putting it into context of what they're saying. So this is how many hours since midnight that it's occurred, and this is how many posts that happens on social media. So 4 hours after midnight would be at 4 a.m. and 14 hours after midnight would be at 2 p.m. So the least amount of posts that occur are at 4 a.m. and 2 p.m. is how I worded it. And then the same could be said about the maximums. The most amount of posts that occur are at noon on a day. And then the next one is 16 hours after midnight. So that's going to put you at 4 p.m. For that next one, which I was kind of shocked at because I figured it'd be more at the evening part. You're going to pause the video and you're going to take a look at this second example to see if you can make sense of it, where you find all of those mins and max. Okay, so you're on a trampoline. They're jumping on a trampoline, trying to perform a somersault. So the first thing I did was list out what all of them are. So min and max. So here was my maximum point. Here is my minimum point. And then the rest I wrote as relative mins and max. I didn't feel like it was necessary to write them all out. So I just kind of wrote a general statement that your least and greatest heights of the athlete, this is just showing the least and the greatest heights of the athlete when those times would occur. So obviously, the more times you're jumping, the greater the height, and then you kind of lost some height as you were continuing on there. All right, last part here is talking about end behavior. And like I said, end behavior is already just your tails, but we're going to write it using infinity and negative infinity. Okay, so it's our behavior of the graph as x approaches positive infinity and negative infinity. So we're going to practice writing using positive infinity as x approaches those and see what happens with our f of x. So it sounds kind of scary, but it's really not that bad. So you're always going to have two answers. You're going to have one where it's saying as x approaches positive infinity, what does our y values do? Which in this case, we just say f of x. And as x approaches negative infinity, what does our y values do? Which in this case is f of x. So it kind of goes off your domain. So as x approaches positive infinity, so here is 0, positive infinity would be going this direction. Where does your graph go? Where your graph goes down. So that means that f of x would be approaching negative infinity. As I'm looking at x goes negative, so as I look this direction from my 0, what does my graph do? My graph goes up, so that means I'm approaching positive infinity. So let's look at the second one. So again, same scenario. You're always going to have x approaching positive infinity and x approaching negative infinity. Doesn't matter the order in which you do it. So this one I just flip-flopped the order. So as x approaches negative infinity, that means I'm looking at going this direction. So what does my graph do? It's going up. So that means that f of x would have to be going towards positive infinity. And as I look as x goes positive, which is going to the right, which way does it go? My graph again is going up, so f of x would approach positive infinity. I want you to try that last graph and see if you can write it out correctly. So on the last graph, as x goes negative infinity, then f of x is going to approach negative infinity as well, because negative infinity would be looking to the left and my graph is going down. As x approaches positive infinity, which is me looking to the right of that axis, my graph is going up, so f of x would be positive infinity. So again, a lot more vocab again with extrema, and then also end behaviors and how do you write it notationally wise. But I think again, if you practice these enough, you'll get the hang of it. Section 1.4 is all about sketching graphs. Here are some vocabulary words that we've already discussed that will still be used. Domain will be your x values, range will be your y values, intercepts are going to be where your graph crosses your x or your y axis. We decided to not talk about symmetry, so you can ignore that piece. End behavior are going to be your tails, which way are those end tails going to face. Extrema is going to be your minimums, your maximums, your relative mins, relative max. Increasing and decreasing is going to show which way your graph is going. So as I go from left to right, is it going up or going down? Positive or negative is going to be where your graph is above or below the x-axis. So in other words, what are your y values doing? Are they going to be positive or negative for a certain value? So they're going to give us some certain criteria, and we're going to have to sketch a graph based off of what we have for this criteria. So I have this example here where it's a y-intercept at 0, -70. I have that it's going to be a linear function. I'm going to be positive for these values that x is less than -30. I'm decreasing for all my values, and then it shows me my end behavior. So the first thing I did is I went ahead and plotted my y-intercept. So on the y-axis, put a point at -70. Then what's going to happen is I look at my end behavior because that's going to show my tails. So as x is going positive, this is showing me that I'm going to end down. And as x is going negative, it's going to go up. So I know that my one on the left is going to be up and the one on the right is going to be down. Then it also tells me that it's going to be linear. So what I did was I went ahead and plotted the point -70 on the y-axis. I knew that my tails were going to go like this, but I didn't know if I had another point somewhere. And I did know that it said that the values of x are positive when I'm less than -30. So at -30, I knew is where I'm going to become positive above the y-axis. So that's how I put all those pieces together. You're going to pause the video and try the got it question. So in the got it question, you have a linear function. So that means I'm going to have a straight line. I'm going to have a y-intercept of 0, 0. My tails, it looks like I'm going to be going up on the right, and on the left, I'm going to be going down. So here's what I drew. I have my y-intercept at 0. My tail is going down on the left, up on the right, and also the x-intercept at 0 says it's going to become positive. So I know at this point is also where it's going to be increasing. Then what happens if it has a different kind of figure where it's not linear? So here's an example of where it's nonlinear. Same kind of scenario, but just giving you more information. So again, what I did was I started with my y-intercept and I put it at 3. I knew that it's continuous, it's positive for all of my values of x, and then it's decreasing at a certain point. I have a minimum at 0, 3. So if I have a minimum, that means that this is going to be at the bottom of my curve. My tails have to be facing up. So since everything is positive and I have to have a minimum, this is how I drew it. So this had to be at the bottom of my valley. My tails had to be facing up. All my y values are above 0, so that makes it work for everything. Pause the video and try the next got it question. Here's another nonlinear function. We see that we have a relative minimum at 1, -6, so I plotted that point here. Then we also know that our tails are both facing up because I have positive infinities. It's increasing from x greater than 1. So at 1 here, I know that I am going upwards, so that's how I drew that part. I know for values x such that x less than -3.5 is where it's going to become positive again. So here's an x-intercept at -3.5. Here's another x-intercept at 1.5. Now the thing that kind of threw me off is that it said relative minimum. So I think that this would be the appropriate graph where this is a minimum, but you're going to have a lower hump down here somewhere before it reaches back up, only because they use the word relative minimum. Okay, then the last example is just doing a real world example, but doing something similar where you're trying to make sense of it. So here's the scenario. Hay is test driving a car she is thinking of buying. She decides to accelerate to 60 miles per hour and then decelerate to a stop to test its acceleration and brakes. Takes her 15 seconds of uniform acceleration to reach her maximum speed and 15 seconds of deceleration to come to stop. Use the key features to sketch a graph. So it tells me that the y is the speed and that the x is the time. Okay? She decides to accelerate to 60 miles per hour and then decelerate to a stop. So that tells me that we are accelerating and then decelerating, so something like that. It takes her 15 seconds to accelerate to reach her maximum speed and 15 seconds to decelerate. So then what I did was I just put in my numbers. So I know my graph is going to look like this. Took me 15 seconds to get here, another 15 to finish. So that puts me at 30 seconds. And then I went ahead and labeled the maximum speed at 60. You're going to pause the video and try the very last one. On the very last one, here is your scenario. And this is what it should look like. So I'm starting at 0 miles per hour. I'm going to continue to jog until the 20th minute, and I'm going to go for 6 miles per hour. I'm going to keep that speed till the 35th minute, and then after that is when I'm going to decrease. So that's why I came back down and stopped at 40. All right, folks, that is it for sketching a graph. It's just putting all that vocabulary together. Section 1.5 is about graphing linear functions and also linear inequalities. So we are going to practice graphing an equation using 3 different methods. You can graph it using a table, using the x and y intercepts, or using the slope-intercept form. The first one we're going to do is look at how to graph it using a table. So first thing is you always want to make sure that it's solved for y. So what I would recommend is trying to move everything that's extra that's not attached to the y. So for example, what I would do is I would minus my x to the other side. So then I have 3y minus 6, and then 0 minus 6. I don't need that 0, so I'm just going to put negative x. And then I'm also going to want to move that 6 over as well. So then I just have 3y equals negative x plus 6. And then I'm going to come through and I'm going to divide everybody by 3. So remember, this is 1 divided by 3, not 3 divided by 1. So this is going to give me a fraction since that top number is smaller. And then I'm going to simplify 6 divided by 3 and get 2. So first step is you want to solve that for y, and that's what this is showing. Next, what you're going to do is make a table of values. Now you can use any x values you want. Typically what people will use is -1, 0, and +1. Okay, those are the usual default values that we want to use. If you have a fraction, it's probably best to use multiples of this. So what I mean by that is instead of using -1, I'm going to use -3. I will still use 0, and then I'll use +3. So if this bottom number was a 4, I would use -4, 0, and 4. Okay, and the reason being is because what you're going to do is you're going to plug in these values, and it's nice to have whole numbers to plot versus dealing with decimals and fractions. So our next step is we're going to plug in these x values to figure out what y is equal to. So -1/3 times -3 plus 2, and then I'm going to type that in my calculator, and I'm going to get my answer of 3. And then I'm going to keep doing that for the rest of them, where I'm going to plug in 0, and I'm going to plug in +3, and then I'm going to get all of my answers. So I'm going to get 2 and 1 for my y values. So what you're doing is you have found points that you can plot. Okay, so to remind you of those points to plot, I would go -3, that means 3 to the left, and then up 3. 0, 2 means I just go straight up 2, and then 3, 1 means I go right 3 and up 1, and then draw your line. Okay, so you can pause the video now and try this next got it question. If I can get my paper to turn, there we go. So there's your next got it question. So what I did to begin with is I subtracted my x over, and I added 7. That's what you're seeing in this step right here. Be careful and make sure you divide everything by -2 because that's going to switch some signs around. So again, this is going to give you a fraction since the top number is smaller. So I'm going to end up with a +1/2 because of double negatives dividing. And then this I'm going to change into a decimal since it's easier to work with. So -3.5. Now what I'm going to do is come up with my table of values. So same as the last, use multiples so that they're matching that denominator. So that's why I would use -2, 0, and +2. And then you would want to plug them into the x value and find the answer. So 1/2 times -2 minus 3.5 would give me -4.5. Then plug in 0. So 1/2 times 0 minus 3.5 is -3.5. And then plug in +2. And then you'll come over here and you'll plot those points. So -2, -4.5, 0, -3.5, and then +2, -2.5, and draw your line. So that's the first method. Not my favorite just because it takes a while. So that's graphing using a table. The next method we are going to do is graphing using intercepts. And if you've ever had me for Algebra 1B before, this is what I call as the cover-up method because it's the easiest to use if you do a cover-up. You can use the cover-up method as long as it's in standard form, which means the x and the y are together on one side. Okay, so if I want to find the x-intercept, I would cover up the y term, and I would write down my equation. So in this case, I would write down 3x equals -12. And then all you have to do to find your x-intercept is just solve that equation. So I would divide by 3 and I would get -4. You can do the same thing to find the y-intercept. You cover up the x term and then write down your equation. So -2y equals -12. Solve that equation and you'll get your y-intercept to 6. So all you need are 2 points. So as long as you're staying along the axes for your intercepts, that's it. So x-intercept at -4, y-intercept at 6, and then just draw your line. Okay, go ahead and pause the video and try the got it question. So in the got it question, do the cover up again. So if you cover it up for your x-intercept, you should be getting -4. If you cover it up to get your y-intercept, you should be getting a +9. So just be careful on signs on that one. So y-intercept is +9, x-intercept is -4, and then just draw your line. I like that method as long as it's in standard form. It's very easy to use. Otherwise, I typically will usually just graph and slope-intercept, which is what we're going to do next. So if I'm in slope-intercept form, that means it has to be solved for y. So y equals mx plus b. Remember, we already talked about this. This is your slope number, so your rate of change. This is your y-intercept. So to begin, I know my y-intercept is going to be at -4. That's always my starting point, finding that point to begin. Okay? Then your next step is to find the next point, and that's where you use your slope to find the next point. So we always need our slope in fraction form because that top number is going to tell me to go up or down, and that bottom number is going to tell me to go to the right. So since my top number is positive, I have +3 that I'm going to go up. So 1, 2, 3, and then my bottom number is +2, so I'm going right 2 and putting a point. You can keep doing that several times and finding multiple points on your graph if you would like. Otherwise, you can just do it for 2 points. All right, go ahead and pause the video and try the last got it question. So in this case, you would want to start at your y-intercept, which is +3. Your slope is -1, so you want to change that into a fraction by putting it over 1. So since my top number was negative, I'm going down 1, and then I'm going right 1. Down 1 and right 1. That's why I always emphasize that bottom number as always going to the right, so that your line is making sure, that it is falling. Okay, so that's part 1 of section 1.5. Part 2 is where we look at inequalities. So we take all of that graphing information, and we're going to apply it to an inequality. So the first thing you need to know is, when do I need to do a solid line or a dashed line? So when we have inequalities, those are those less than or greater than symbols. So if it has an equal sign underneath it, you're going to draw just a normal line. If it's missing that equal sign, we're going to do a dash line to show that that line is not being included. Okay? Now, typically some books will want you to test a point in order to see which side you're going to shade. So after you get done graphing your line, you're going to have to shade above or below it. If I am a less than, okay, I'm going to find my y-intercept and I'm going to shade everything below that. So that would be showing less than. If I am greater than, that means I want to shade everything above. So find your y-intercept and you're going to shade everything above that line. So let's make sense of this. So here's my inequality. Okay? What we have to do first is change it into slope-intercept form. So here is my y. I need to get rid of this guy and this guy. So since this is attached to the y, I'm going to start here. So my first step of doing it would be minusing my 12 to the other side. And that's where I'm getting this inequality. Next, I'm going to divide everything by -4. So just like we practiced before. Now remember, this is going to give you -1/4 because the top number is smaller, so I have a fraction. And then be careful of signs here. Negative divided by negative is going to make it +3. Now, one thing I need you to note with this is when you are doing multiplication and division with inequality symbols, anytime that you multiply or divide by a negative, we have to flip this symbol. And that is the only catch to my little trick of you shading stuff, is you have to remember that. Otherwise, you will shade the wrong side. Okay, so I have to put it in slope-intercept, and I have to remember when I'm dividing by a negative, I got to flip that symbol. So here we just plot our points like normal. So I'm going to go to my y-intercept of 3. My slope is negative, so I'm going down 1, and I'm going right 4. Since I don't have that equal bar underneath there, that's why I'm drawing a dashed line. Since it's a less than symbol, I'm shading everything below my y-intercept. So here's my y-intercept. That's why I'm shading everything below. So this would be my final answer. Pause the video and see if you can try this next one. So this one seems kind of messy because they gave you some decimals in there, but it cleans up nicely after you solve it. So I would add that 7 over first. That's where you get this part. And then I would divide everything by -3.5. So first thing, I divided by negative, so flip your symbol. Then these simplify nicely. So it's -3x and then -2. So you're going to start at -2 on the y-axis. You're going to go down 3 and right 1 for your slope. I don't have a bar underneath my inequality, so it's a dashed line. It is a less than symbol, so find your y-intercept. I'm shading everything below that line, so that means I'm shading this side to the left. Okay, here's just another example if you wanted to take a look at it. Doing the same kind of thing, but now you have a solid line. So still solve it for slope-intercept. So I'm going to minus my 9 over, and I'm going to divide by 3. So this is what I got. I didn't have to flip my symbol this time because I didn't divide by negative. So this is just going to stay as is. So I'm going to start at -3 on the y-axis. I'm going to go up 8 and right 3. This time we get a nice solid line. So from that equal sign, since it's a less than, I'm finding my y-intercept and I'm shading everything below, which is why we would shade this side of the line. All right, if you need another practice problem, you can try this guy right here. If you tried this guy, here is what you would get. I would add my 12x and divide everybody by 3, so this is your inequality. So you're at 2 going up 4 over 1. It is a nice solid line with that equal sign, and then I'm doing greater than. So here's my y-intercept. I'm shading everything above my y-intercept. And then we have one more example where it just shows what would happen if I had in a real world situation. So the final grades for an algebra class are calculated by combining test grades and homework grades. The following inequality represents a student who wants to learn earn higher than a 90% overall. Graph the inequality. So same kind of scenario, they just want you to graph it. So here is me showing how I would solve it for y. So I subtracted my 0.7x over first, divided everybody by 0.3. So nothing is going to flip for your symbol. So then I started on my y-intercept, and I did change this to fraction form because you want your slope to be as a fraction. So I started on my y-intercept of 3. I went down 7 and right 3. And then I did a dash line with no inequality. And since it's greater than, I found my y-intercept and I shaded everything above that line. All right, folks, that takes care of graphing linear functions and linear inequalities. It's quite extensive because you show all three methods of how to graph along with how to graph those inequalities.